We have seen in the previous standard that the gravitational force is a universal force, and it acts not only between two objects on the Earth but also between any two objects in the universe. Let us now learn how this force was discovered. Gravitation. As we have learned, the phenomenon of gravitation was discovered by Sir Isaac Newton. As the story goes, he discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downward and not at an angle to the vertical. Why do they not fly off in a horizontal direction? After much thought, he came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is the vertical direction at the position of the apple, and thus the apple falls vertically downwards. Figure 1.1. On the left shows an apple tree on the earth. The force on an apple on the tree is towards the center of the earth, that is, along the perpendicular from the position of the apple to the surface of the earth. The figure also shows the gravitational force between the earth and the moon. The distances in the figure are not according to scale. Newton. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the earth, can it also act on objects at even greater heights, much further away from the earth, like for example the moon? Can it act on even farther objects like the other planets and sun? Force and motion. We have seen that a force is necessary to change the speed as well as the direction of motion of an object. Introduction to scientist. Great scientist Sir Isaac Newton, 1642 to 1727, was one of the greatest scientists of recent times. He was born in England. He gave his laws of motion, equation of motion, and theory of gravity in his book Principia. Before this book was written, Kepler had given 3 laws describing planetary motion. However, the reason why planets move in the way described by Kepler's law was not known. Newton, with his theory of gravity, mathematically derived Kepler's law. In addition to this, Newton did groundbreaking work in several areas including light, heat, sound, and mathematics. He invented a new branch of mathematics. This is called calculus, and has wide-ranging application in physics and mathematics. He was the first scientist to construct a reflecting telescope. Circular motion and centripetal force. Tie a stone to one end of a string. Take the other end in your hand and rotate the string so that the stone moves along a circle as shown in figure. Are you applying any force on the stone? In which direction is this force acting? How will you stop this force from acting? What will be the effect on the stone? As long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle, and are applying a force towards it. The force stops acting if we release the string. In this case, the stone will fly off along a straight line, which is the tangent to the circle at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time. You may recall that we have performed a similar activity previously, in which a 5-rupee coin kept on a rotating circular disc flies off the disc along the tangent to the disc. Thus, a force acts on any object moving along a circle, and it is directed towards the center of the circle. This is called the centripetal force. Centripetal means center-seeking, that is, the object tries to go towards the center of the circle because of this force. You know that the moon, which is the natural satellite of the earth, goes around it in a definite orbit. The direction of motion of the moon as well as its speed constantly changes. during this motion? Do you think some force is constantly acting on the moon? What must be the direction of this force? How would its motion have been if no such force acted on it? Do the other planets in the solar system revolve around the Sun in a similar fashion? Is similar force acting on them? What must be its direction? From the above activity, example and questions, it is clear that for the moon to go around the earth, there must be a force which is exerted on the moon. And this force must be exerted by the earth, which attracts the moon towards itself. Similarly, the Sun must be attracting the planets, including the earth, towards itself. Kepler's law. Planetary motion had been observed by astronomers since ancient times. Before Galileo, all observation of the planet's position were made with naked eye. By the 16th century, a lot of data were available about planetary positions and motion. Johannes Kepler studied this data. He noticed that the motion of planets follows certain laws. He stated 3 laws describing planetary motion. These are known as Kepler's law, which are given below. An ellipse is the curve obtained when a cone is cut by an inclined plane. It has 2 focal points. The sum of the distances to the 2 focal points from every point on the curve is constant. F1 and F2 are 2 focal points of the ellipse shown in figure. If A, B and C are 3 points on the ellipse, then AF1 plus AF2 is equals to BF1 plus BF2 is equals to CF1 plus CF2. Kepler's first law. The orbit of a planet in an ellipse with the Sun at one of the foci. Figure shows the elliptical orbit of a planet revolving around the Sun. The position of the Sun is indicated by S. Kepler's second law. The line joining the planet and the Sun sweeps equal areas in equal intervals of time. AB and CD are distances covered by the planet in equal time, that is, after equal intervals of time. The positions of the planet starting from A and C are shown by B and D respectively. The straight lines AS and CS sweep equal area in equal interval of time, that is, area of ASB and CSD are equal. Kepler's third law. The square of its period of revolution around the Sun is directly proportional to the cube of the moon, distance of a planet from the Sun. Thus, if r is the average distance of the planet from the Sun and t is its period of revolution, then T2a r3, that is T2 upon r3 is equals to constant is equals to k. Kepler obtained this law simply from the study of the position of planets obtained by regular observation. He had no explanation as to why planets obey these laws. We will see below how these laws helped Newton in the formulation of his theory of gravitation. Newton's universal law of gravitation. All the above consideration, including Kepler's law, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. An introduction to scientists. Johannes Kepler, 1571 to 1630, was a German astronomer and mathematician. He started working as a helper to the famous astronomer Tycho Brahe in Prague in 1600. After the sudden death of Brahe in 1601, Kepler was appointed as the royal mathematician in his place. Kepler used the observation of planetary position made by Brahe to discover the laws of planetary motion. He wrote several books. His work was later used by Newton in postulating his law of gravitation. Figure shows two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as Fa m1 m2 upon d2, or F is equals to G m1 m2 upon d2. Here G is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of an object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If the two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. In case when the bodies are not spherical or have irregular shape, then the direction of force is along the line joining the centers of mass, and d is taken to be the distance between the two centers of mass. From equation, it can be seen that the value of G is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of G is equal to the gravitational force between two masses of 1 kg kept 1 m apart. Use your brain power. Show that in SI units, the unit of G is Newton, m2, kg minus 2. The value of G was first experimentally measured by Henry Cavendish. In SI units, its value is 6.673 into 10 raised to minus 11 and m raised to 2 kg raised to minus 2. Uniform circular motion, magnitude of centripetal force. Consider an object moving in a circle with constant speed. We have seen earlier that such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle. This force is called the centripetal force. If m is the mass of the object, v is its speed, and r is the radius of the circle, then it can be shown that this force is equal to F is equals to m v raised to 2 upon r. If a planet is revolving around the sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the sun must be F is equals to mv square upon r, where m is the mass of the planet, v is its speed, and r is its distance from the sun. The speed of the planet can be expressed in terms of the period of revolution t as follows. The distance traveled by the planet in one revolution is equals to perimeter of the orbit 2 pi r. R is equals to distance of the planet from the sun. Time taken is equals to period of revolution is equals to t. V is equals to distance traveled upon time taken is equals to 2 pi r upon t. F is equals to mv square upon r is equals to m in bracket 2 pi r upon t bracket close square is equals to 4m pi square r upon t square. Multiplying and dividing by r square, we get F is equals to 4m pi square upon r square is equals to in bracket r cube upon t square bracket close. According to Kepler's third law, t square upon r cube is equals to k. F is equals to 4m pi square upon r square k, but 4m pi square upon k is equals to constant. Thus, Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified this force with the force of gravity and hence postulated the inverse square of gravitation. The gravitational force is much weaker than other forces in nature, but it controls the universe and decides its future. This is possible because of the huge masses of planets, stars, and other constituents of the universe. Do you know? You must be knowing about the high and low tides that occur regularly in the sea. The level of sea water at any given location along sea shore increases and decreases twice a day at regular intervals. High and low tides occur at different times at different places. The level of water in the sea changes because of the gravitational force exerted by the moon. Water directly under the moon gets pulled towards the moon, and the level of water there goes up, causing high tide at that place. At two places on the earth at 90 degrees from the place of high tide, the level of water is minimum and low tides occur there as shown in figure. Earth's gravitational force. Will the velocity of a stone thrown vertically upwards remain constant, or will it change with time? How will it change? Why doesn't the stone move up all the time? Why does it fall down after reaching a certain height? What does its maximum height depend on? The earth attracts every object near it towards itself because of the gravitational force. The center of mass of the earth is situated at its center. So the gravitational force on any object due to the earth is always directed towards the center of the earth. Because of this force, an object falls vertically downwards on the earth. Similarly, when we throw a stone vertically upwards, this force tries to pull it down and reduces its velocity. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downward towards the center of the earth under its influence. Earth's gravitational acceleration. The earth exerts gravitational force on objects near it. According to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the earth on a body results in its acceleration. This is called acceleration due to gravity and is denoted by g. The direction of the acceleration due to gravity is also directed towards the center of the earth, that is, vertically downwards. Value of g on the surface of the earth. We can calculate the value of g by using Newton's universal law of gravitation for an object of mass m situated at a distance r from the center of the earth. The law of gravitation gives F is equals to gm m upon r square. M is the mass of the earth. F is equals to mg. mg is equals to gm m upon r square. G is equals to gm upon r square. If the object is situated on the surface of the earth, r is equals to radius of the earth. Thus, the value of g on the surface of the earth is g is equals to gm upon r square. The unit of g in SI units is m upon s square. The mass and radius of the earth are 6 into 10 raised to 24 kg and 6.4 into 10⁶ and 6.4 into 10 raised to 6 m respectively. Using this in g is equals to 6.67 into 10 raised to minus 7 into 6 into 10 raised to 24 upon in bracket 6.4 into 10 raised to 6 bracket close square is equals to 9.77 m upon s square. This acceleration depends only on the mass m and the radius r of the earth, and so the acceleration due to gravity at a given point on the earth is the same for all objects, does not depend on the properties of the object. Variation in value of g. Point A. Change along the surface of the earth. Will the value of g be the same everywhere on the surface of the earth? The answer is no. The reason is that the shape of the earth is not exactly spherical, and so the distance of a point on the surface of the earth from its center differs somewhat from place to place. Due to its rotation, the earth bulges at the equator and is flatter at the poles. Its radius is largest at the equator and smallest at the poles. The value of g is thus highest in bracket 9.832 m upon s square bracket close at the poles and decreases slowly with decreasing latitude. At the poles and decreases slowly with decreasing latitude. It is lowest in bracket 9.72 m upon s square bracket close at the equator. Point B. Change with weight. As we go above the Earth's surface, the value of r in equation increases and the value of g decreases. However, the decrease is rather small for heights which are small in comparison to the Earth's radius. For example, remember that the radius of the Earth is 6,400 km. If an aeroplane is flying at a height 10 km above the surface of the Earth, its distance from the Earth's surface changes from 6,400 km to 6,410 km, and the change in the value of g due to it is negligible. On the other hand, when we consider an artificial satellite, do you know gravitational waves? Waves are created on the surface of water when we drop a stone into it. Similarly, you must have seen the waves generated on a string when both its ends are held in hand and it is shaken. Light is also a type of wave called the electromagnetic wave. Gamma rays, X-rays, ultraviolet rays, infrared rays, microwave and radio waves are all different types of electromagnetic waves. Astronomical objects emit these waves and we receive them using our instruments. All our knowledge about the universe has been obtained through these waves. Gravitational waves are a very different type of waves. They have been called the waves on the fabric of space-time. Einstein predicted their existence in 1916. These waves are very weak and it is very difficult to detect them. Scientists have constructed extremely sensitive instruments to detect the gravitational waves emitted by astronomical source. Among these, LIGO in bracket laser interferometric gravitational wave observatory bracket close is the prominent one. Exactly after 100 years of their predictions, scientists detected these waves coming from an astronomical source. Indian scientists have contributed significantly in this discovery. This discovery has opened a new path to obtain information about the universe. Free fall. Take a small stone, hold it in your hand, which forces are acting on the stone. Now release the stone. What do you observe? What are the forces acting on the stone after you release it? We know that the force of gravity due to the earth acts on each and every object. When we were holding the stone in our hand, the stone was experiencing this force, but it was balanced by a force that we were applying on it in the opposite direction. As a result, the stone remained at rest. Once we release the stone from our hands, the only force that acts on it is the gravitational force of the earth, and the stone falls down under its influence. Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in a free fall. In free fall, the initial velocity of the object is zero, and goes on increasing due to the acceleration due to gravity of the Earth. During free fall, the frictional force due to air opposes the motion of the object, and the buoyant force also acts on the object. Thus, true free fall is possible only in vacuum. For a freely falling object, the velocity on reaching the Earth and the time taken for it can be calculated by using Newton's equation of motion. For free fall, the initial velocity u is equals to 0 and the acceleration a is equals to g. Thus we can write the equations as v is equals to gt, s is equals to 1 upon 2 g t square, v square is equals to 2 gs. For calculating the motion of an object thrown upwards, acceleration is negative, that is in a direction opposite to the velocity, and is taken to be negative g. The magnitude of g is the same, but the velocity of the object decreases because of this negative acceleration. The moon and the artificial satellites are moving only under influence of the gravitational field of the Earth. Thus they are in free fall. Do you know the value of g is the same for all objects at a given place on the Earth? Thus any two objects, irrespectively of their masses or any other properties, when dropped from the same height and falling freely, will reach the Earth at the same time. Galileo is said to have performed an experiment around 1590 in the Italian city of Pisa. He dropped two spheres of different masses from the Leaning Tower of Pisa to demonstrate that both spheres reached the ground at the same time. When we drop a feather and a heavy stone at the same time from a height, they do not reach the Earth at the same time. The feather experiences a buoyant force and a frictional force due to air, and therefore floats and reaches the ground slowly, later than the heavy stone. The buoyant and frictional forces on the stone are much less than the weight of the stone and does not affect the speed of the stone much. Recently, scientists performed this experiment in vacuum and showed that the feather and stone indeed reach the Earth at the same time. Gravitational potential energy. We have studied potential energy in last standard. The energy stored in an object because of its position or state is called potential energy. This energy is relative and increases as we go to greater heights from the surface of the Earth. We had assumed that the potential energy of an object of mass m at height h from the ground is mgh, and on the ground it is 0. When h is small compared to the radius r of the Earth, we can assume g to be constant and can use the above formula mgh. But for large values of h, the value of g decreases with increases in h. For an object at infinite distance from the Earth, the value of g is 0, and Earth's gravitational force does not act on the object. So it is more appropriate to assume the value of potential energy to be 0 there. Thus, for smaller distances, that is heights, the potential energy is less than 0, that is, it is negative. When an object is at a height h from the surface of the Earth, its potential energy is minus gmm upon r plus h. Here, m and r are Earth's mass and radius respectively. Escape velocity. We have seen then when a ball is thrown upwards, its velocity decreases because of the gravitation of the Earth. The velocity becomes 0 after reaching a certain height, and after that the stone starts falling down. Its maximum height depends on its initial velocity. According to Newton's third equation of motion is v square is equals to u square plus 2as. V is equals to the final velocity of the ball is equals to 0 and a is equals to minus g. Therefore, 0 is equals to u square plus 2 in bracket minus g bracket close s, and maximum height of the ball is equals to s is equals to minus u square upon 2g. Thus, higher the initial velocity u, the larger is the height reached by the ball. The reason for this is that the higher the initial velocity, the ball will oppose the gravity of the Earth more, and larger will be the height to which it can reach. We have seen above that the value of g keeps decreasing as we go higher above the surface of the Earth. Thus, the force pulling the ball downward decreases as the ball goes up. If we keep increasing the initial velocity of the ball, it will reach larger and larger heights and above a particular value of initial velocity of the ball. The ball is able to overcome the downward pull by the Earth and can escape the Earth forever and will not fall back on the Earth. This velocity is called escape velocity. We can determine its value by using the value of conservation of energy as follows. An object going vertically upward from the surface of the Earth having an initial negative velocity equal to the escape velocity escapes the gravitational force of the Earth. The force of gravity being inversely proportional to the square of the distance becomes zero only at an infinite distance from the Earth. This means that for the object to be free from the gravity of the Earth, it has to reach infinite distance from the Earth. That is, the object will come to rest at infinite distance and will stay there. Do you know weightlessness in space? Space travelers as well as objects in the spacecraft appear to be floating. Why does this happen? Though the spacecraft is at a height from the surface of the Earth, the value of g there is not zero. In the space station, the value of g is only 11% less than its value on the surface of the Earth. Thus, the height of a spacecraft is not the reason for their weightlessness. Their weightlessness is caused by their being in the state of free fall, though the spacecraft is not falling on the Earth because of its velocity along the orbit. The only force acting on it is the gravitational force of the Earth, and therefore it is in a free fall, as the velocity of free fall does not depend on the properties of an object. The velocity of free fall is the same for the spacecraft, the travelers, and the objects in the craft. Thus, if a traveler releases an object from her hand, it will remain stationary with respect to her and will appear to be weightless.